So I'm one of the leaders hosting the review today. I'm a PLTL leader and I'm a sophomore. And then I have another co-host.
All right, and my name is Neha Paramala, and I am a junior, and I am a PLTL leader as well.
So we're gonna get started. The plan for today is to start with kinetics, which I'll be covering, and then we're gonna move on to equilibrium, which Neha will take over. And then lastly, we're gonna go into breakout rooms, and we have a set of 16 questions we're gonna practice. And the leaders of the breakout rooms are gonna be me, Neha, and two more other Student Success Center leaders. So let's get started on the first topics, kinetics. So kinetics is all about how fast a reaction occurs, which is a little different than what you've been talking about before in chemistry. Up until kinetics, a lot about chemistry has been about how much of something you're making. So it's been how much moles, it's been how much atoms, it's been how many grams. But now we're more worried about how fast. And that's a super important concept too. Because, for example, let's say I'm a scientist and I want to make a cancer drug. And I know I can make a lot of this cancer drug. But if it takes me 100 million years to make, is it really a practical drug to make, even if I can make a bunch of it? No, right? So it's really important to know how fast a reaction is happening, not just how much of the reaction products we're making. So we describe reactions with the kinetics with rate laws. And we write rate laws in this format written up here. So we can say rate expressed as molarity over seconds is equal to K. And notice that this K is a small k. It's not the big K of equilibrium. There are two different Ks. And you're going to multiply that by some concentration of compound A raised to some exponent times some concentration of compound B raised to another exponent. And it's important to note that this little k has units, and these units depend on the general order of the rate. So, for example, if we have a first order, we'll see a 1 over seconds for the units of k. Second order, 1 over molarity times second, and third order, 1 over molarity squared times seconds. So you have to make sure what order of rate you have before you can figure out the units of k. And just to note, when you're looking at order, you're going to be adding the exponents for your concentrations. So let's say x here equals 1 and y here equals 2, then you'd have an order of 3. And also, when you see something with an exponent of 1, usually you won't actually see that 1 written, right? Usually it'll just be the concentration, and it's going to have an implied 1. So don't forget it's still there, though. So I have an example right over here of a reaction, which is the formation of carbon tetrachloride. So what's wrong with this rate that I have written under it? Yeah. So let's say this is not, yeah, there's a solid, exactly. You don't want to include any solids. And then let's say this is not an elementary step. This is a total reaction. Could I just take the coefficient? No, I can't take coefficients. Only for a rate limiting slowest step can I take the coefficients and just plop them onto my rate, right? So there's a lot wrong with this rate. How do we determine rates? Usually. Through data, through experiments. You'd be in the lab and at a graph in your classes or on your exam that compares different rates and different initial concentrations. And Later on in this packet, you're going to see a practice problem where you have to determine the rate experimentally, or with a rate determining step. So the rate determining step, just a reminder, is going to be your slowest step, and that's the only time you can write and rate law using the coefficients if it's a slowest step. And they'll tell you if it's the slowest step. If it doesn't say it, then assume it's a total reaction. So next we have integrated rate laws. And they're really useful because they allow us to write rates of a certain order in the form of y equals mx plus b. So our k, for example, for zero order means that we have a negative slope and it represents m. Then our initial concentration, that's going to be our b. Our y is going to be the final concentration, and t is going to be our x. And we can also have a half-life formula we derive from these integrated rate laws. And it's really important that you guys know these formulas because you're going to definitely have questions testing you on them or testing you on the concept. And your professors are not going to give them to you. So I recommend studying up on this and doing some practice. They can be a little tricky to know. And you have to make sure you know which one is a zero order, which one's the first order, and which one's the second order. They're not going to go above second order, though, for the integrated rate laws. And then on the next slide, I have an example of why it's useful. So let's say we did an experimental lab, and I found concentrations at some time, and then I took that concentration, and then I multiplied by ln for the second one, and then I put it as the denominator for the third one. Yeah, which of the following represents the order of the reaction? Yeah, a second order, and it's going to be this third graph right over here. So the first one is a zero order, the second one is a first order, and then the third one is a second order. And how do we know this is a second order rate? Yeah. Also, it's the slope, right? That it's linear. Whenever the rate is appropriate for that integrated rate law, you're going to see the slope becoming linearized. And this is a super useful strategy we have for taking our experimental data and identifying the order. And then usually from this data and order we come up with, then we could think of the mechanisms. So next, I'm going to discuss the Arrhenius equation. So the Arrhenius equation is helpful because it shows the relationship between our K value and temperature. So there are two ways you can really write this out. You can write it in this formula with it as an exponent, and then you could change it into a y equals mx plus b format as well. So written like the y equals mx plus b format, what represents the slope here? Yeah, exactly. It's going to be negative EA over R. And then what about the y-intercept? Yeah. So, for example, they could give you a graph that shows something related to the Arrhenius equation. And they might ask you to find or figure out some aspect of it based on your knowledge of this formula written in y equals mx plus b. They might be like, okay, well, now I want to know, I don't know, the negative EA over R, and you have to know that's like the slope, and then maybe you could take that and figure out something else. So it's really important to understand what each component represents. Also, don't worry about knowing the constant. The constant will be given to you. I do want to note, though, that the constant includes Kelvin, and that's why your temperature is always going to be in Kelvin. Don't forget, if you have a problem like this, to convert your temperature to Kelvin. It's probably one of the most missed things about like problems like this, forgetting to convert. Okay, so next we're going to talk about reaction mechanisms, and that's basically how a reaction occurs. So, for example, I'm in school, and the teacher gives me a project to work on, right? We don't do that project in one step, especially if it's a group project, right? If there's a group, maybe one person takes the script writing for the project, another person makes the PowerPoint, another person, I don't know, makes advertisements for the project. So every person has their own component of the project. So that's the elementary steps. And then the final project is going to be your total reaction. So going with this analogy, the person who takes the longest to complete their job is going to be the rate determining slowest step of the project. Because even if we could make one of the other people faster, you can't turn in your final project until everyone's done, right? So making the faster steps faster is not going to change your rate. Only modifying the slowest step will. And so that's the concept of why our slowest step is the rate determining. So right over here, we have an example of a mechanism. So C here is an intermediate, and we know it's an intermediate because it's being created in an elementary step, and then it's being consumed in an elementary step. E, however, is a catalyst. And we know E is not an intermediate, but a catalyst because we start with E. And unlike C, E ends up in the end too. You don't use up a catalyst. A catalyst remains. We don't want a catalyst to be on our final reaction. So in the lab, what will happen is you filter your catalyst out. It's not really a relevant product because we added that in and it didn't do anything to our concentrations. A catalyst just makes a reaction go faster. And how does it do that? Yeah, it lowers EA, activation energy, exactly. So some rules about reaction mechanisms to determine if a reaction mechanism is actually appropriate for the given reaction. So in a lab, again, when we determine our experimental rate law, when we make up our reaction mechanisms, we don't know for sure that this reaction mechanism is necessarily how it happens. So when we are checking the reaction mechanism we come up with, we have to keep in mind that the sum of the elementary steps has to be equal to the overall balance equation. So even if all the compounds are the same, but it won't balance in the same amount, then you have to look back at your reaction mechanism. So there has to be something wrong there. And then the second rule is that your rate determining step must have the same rate law as the experimentally determined rate. So for example, if your slowest step gives you a rate law that has an intermediate in it, you might have to do some substitution in order to get rid of your intermediate and make it equal the experimentally determined rate. Because your experimentally determined rate is not going to have an intermediate in it. And we have an example problem where you'll have to do some substitution to make them equal back in the end of this. So don't worry, we'll get some practice with that. And the last topic I'm going to cover is catalysts. So you have two kinds. You have heterogeneous catalysts and you have homogeneous catalysts. Heterogeneous catalysts are in a different state of matter than the reactants. So for example, if your reactants are gases, then your catalyst might be a solid. And solids are really good as catalysts when we're talking about heterogeneous catalysts because they can be filtered out easily. So if you're thinking of like, I don't know, for example, a sieve. C catches your solid but allows, liquid gas to go through. And then homogeneous catalysts are in the same state of matter as the reactants. So if the reactants are gases, the catalyst will also be a gas if it's a homogeneous catalyst. And these are good because they're cheaper. They can function selectively. So if you just wanted to function on one step of the mechanism, the one we really care about is the rate determining slowest step. And then it minimizes the decomposition of product at high temperatures. So it increases our yield. And then enzymes are an example of biological catalysts. And they're super useful because we don't want the things in our body to happen slowly. We want our body to be able to function efficiently and maintain homeostasis. And without enzymes, we wouldn't be able to have our body do its reactions at a quick enough rate.
All right, so now we're going to go ahead and talk about equilibrium. And equilibrium is related to kinetics in a way in which kinetics kind of, as Jessica had mentioned, tells you the speed of the reaction, but equilibrium will not tell you the speed of the reaction. So don't get that confused with kinetics, but equilibrium will instead tell you the concentrations of each of the reactants and each of the products at equilibrium. And so first we're going to go ahead and talk about the concept of equilibrium. So basically it is a dynamic process where the rate of the forward reaction equals the rate of the reverse reaction. And usually you can tell this because they will be indicated by double-headed arrows, which will kind of tell you like, oh, this reaction is in equilibrium, so the rate of the forward must equal the rate of the reverse. And since they are equal, that means the composition of the system no longer kind of changes. So the composition of the reactants, like the concentration, is just going to be like constant or consistent over time. It's not really changing that much. And then we're going to talk about the equilibrium constant and the reaction quotient. So the equilibrium constant is denoted by Kc, and the reaction quotient is denoted by Qc. And Kc kind of tells you what the reaction is at equilibrium, and Qc kind of tells you at any given point in the reaction. So QC could tell you at equilibrium, but you wouldn't really say QC in that case, you would just say KC. But that is kind of what the difference is between QC and KC, but for both of them, they would be at a constant temperature, and they are both always going to be your products over your reactants, and you will only include gases and aqueous substances in your equilibrium expression, and no solids or liquids will be in there. And I don't think they will necessarily test you guys on why solids and liquids will not be in the reaction, but make sure that you don't put them in the reaction. But if you guys did want to know kind of why that is the case, it is because you always want things in your equilibrium expression that has concentrations that change. And solids and liquids are actually different in which they don't have concentrations that change. And if you think about it in this way, let's say you have a solid cube. And let's say your solid cube has 8 moles. And the volume of that cube is 4 liters. And let's say you cut that cube in half. And now that cube is twice less. So now your new moles is 4, and your volume will also be twice lowered, so it would be 2. And in that case, your concentration, your molarity is moles over liters, correct? So with the full cube, your molarity was 8 over 4. So 8 divided by 4, which is 2. And then your halved cube is 4 divided by 2, which is still 2 molarity. So just think about kind of how like proportions and ratios play a role in how solids and liquids do not have concentrations that change. All right, and then moving on, I wrote this reaction down and I was just wanting to write down the Kc and the Qc to show you guys that Kc and Qc will be written the exact same way. It's just going to be products over reactants. And who can tell me why I did not include B in my Kc or my Qc? Exactly. It is a liquid, so it does not belong in your equilibrium expression, only aqueous and gases. And in this case, you will use your coefficients as your exponents. So as you can see, I put my 4 as my coefficient here, so I put it as my exponent. And then the same thing with D, and then the same thing with A. And then what I did for this next reaction, it is the same exact reaction, but what did I do to it? Exactly, yeah. I multiplied everything by 2. So now it's just 4, 6, 8, and 10. So now this new KC, I just denoted it as KC2, and I put the new exponents and coefficients. So I put C to the 8, and then D to the 10, and then A to the 4. So now my KC2 is actually going to be my KC squared. And yes, if I do divide by 2, then it is to the power of half. And so basically, if you look at this, yeah, if, instead of 2, this would be half if I divided everything by 2. So basically, if I have a numerical value, let's say my KC was 10, who can tell me what my new KC would be if it was doubled, like I had in this equation? Like, tell me the numerical value. Exactly. And let's say my numerical value for K in this situation is 25. Let's say we went ahead and divided everything by 2. What would my new numerical value be for KC? Exactly. You guys are on the ball. So yeah, that's exactly what you do. You just change your coefficient of, you just change like what you raise to the power for KC, what based on what you're multiplying by or based on what you're dividing by. All right. And then for this one, I also changed it. Who can tell me what I did differently? Exactly. So I just flipped the original reaction, and this was the one that I flipped from the original. So not the one that I multiplied by 2. This is just based on my first KC reaction. And so now it is going to be different in where the products is now going to be A, and the reactants are now C and D. So basically my KC reaction, my new one, KC3, will be flipped. So now the numerical value will be also flipped. So let's say our numerical value for K originally was 10. What would be the new KC with this new change? Exactly. That's exactly right. All right. So this one, I put them all as gases, and the reason I did that was because I just wanted to show you what your Kp would look like. And based on your Kc, it still would be the exact same, and this time we did include B since it is a gas. And your Kc would be exactly the same. You just put brackets as usual. You don't do anything different than what you did with your aqueous substances. But for your Kp, you always want to make sure that the only thing in your Kp is gases. So these are reactions where mainly there are gases, but you also want to make sure that if it does have a solid, liquid, or aqueous, that you don't include it in your Kp. So again, Kc is going to be aqueous and gases are allowed. And for Kp, only gases are allowed. And this is kind of a different way that you would write it. You wouldn't put brackets. You would actually put a big P and then put like a lowered C, D, A, B for your reactants products. And then you would kind of put parentheses over that whole thing and then raise it to your given coefficient for your exponent. All right, and this is the equation where they kind of relate Kp to Kc. So that would be your Kp equals Kc times RT, and that whole squared to the delta, or whole to the power delta n. And in this case, your R is 0.08206, your temperature is in Kelvin, and your delta n is just going to be your moles of products minus moles of reactants. And when I say moles in this case, it's just referring to your coefficients. So it's not talking about like molar mass or anything. You don't have to convert anything like that. It's just what your coefficients are. So keeping in mind what delta n is, who can tell me what the delta n would be of this reaction? Yeah, exactly. It's 4. And so the specific moles that are excluded, you only want to put moles of gaseous products minus moles of gaseous reactants. So again, only we're talking about gases right now when you're talking about Kp. Yeah. And also, I included this, so when delta N equals 0, that is when Kp equals Kc. So if you ever wanted to like find an instance where Kp equals Kc, if they do ask you a question, then it's just when 0 is delta N, because if delta N is 0, what does that make the value of RT? Exactly. So since that is just 1, that makes Kc times 1 is just Kc. So that would just equal Kp. All right, and now we're going to be talking about calculating Kc and Qc. And if all values for concentration are given for each product and reactant at either equilibrium or currently, then you just plug in the values into your specified equilibrium expression. So if they say, like, let's go back to this reaction. So let's say they give you the concentrations for A, B, C, and D, and they say these are the values at equilibrium. Then you would go ahead and set up a Kc expression, plug in those values, and that is your Kc value. But let's say they give you the values for A, B, C, and D, and say this is when the equation is, or the reaction is currently at a given point in time, and they give you a Kc value. So that means the equilibrium expression is, or the reaction is not at equilibrium yet. So now you want to find your QC because it's not at equilibrium. So you do the same thing, you set up your QC expression the same way as you would set up your KC expression, and then you plug in the values, same thing, and then that is now your QC expression. So let me go back to the slide we were on. All right, yeah, so that would be your QC expression. And if some values are given and some are not, then you need to use a Rice table. And what I mean by that is sometimes they will give you like the values of the reactants and say, let's say you added this amount of A and this amount of B, and then you had an amount of D at equilibrium. So you're not really given all the values, you're not given how much you have of A or B at equilibrium, and basically you will need to use a Rice table to figure out what concentration of B or A you have at equilibrium. And I also wanted to mention that if they sometimes give you a reaction and they'll say, well, the K forward of this reaction is this value and the K reverse of this reaction is this value. And sometimes they'll ask you to find the equilibrium constant, and all you really need to do is do K forward divided by K reverse. And make sure that these are little k's, and this one is your big K because it is your equilibrium constant. So yeah, all you need to do here is just divide the two, and make sure it's always forward over reverse. All right, and then this slide I kind of showed you like what would happen based on specific values of Q if it was in relation to K. So if Q is greater than K, then the reaction will shift left or towards the reactants. And if Q is less than K, the reaction shifts towards the right or towards the products. And obviously, if they're equal to each other, basically nothing happens since it's already at equilibrium. But a cool way to kind of remember this is I always like to put my K's on this side, and then I always like to put Q's on this side because then I'm able to do this, and I just draw a line right here because it'll show me which way the reaction kind of shifts if you're unsure. And this way it shows you if Q is greater than K, then this arrow shows that it's going to the left. And if Q is less than K, then this arrow shows that it's going to the right. And another way to kind of show you is through a kind of like a number line type of thing where 0 is K or at equilibrium is K. And let's say your Q is greater than K. So it's like up here or like over here to the right. And so it's always wanting to go back to K, back to the starting point, back to equilibrium. So it will shift this way. So that is shifting it to the left. But let's say Q is less than K. Then it always wants to go back to equilibrium again. So it would shift this way or to the right. So that's kind of like what I wanted to show you guys in this slide. And then, so now we're going to be talking about Le Chatelier's principle. And for reactions that shift to the left, that is kind of when you're adding a product or removing a reactant. And if you're shifting to the right, that means you have removed a product or you have added a reactant. And this will always be the case if you do adding a product or removing a reactant, this will always shift to the left. And in this case, it'll always shift to the right. But for sometimes it'll depend, and that's when your reaction kind of depends whether it's endothermic or exothermic, because if you're adding heat and it's an endothermic reaction, it will shift to the right because your heat is on your reactant side. So again, you're like adding a reactant, so shifting to the right. But if it's an exothermic reaction, your heat is actually on the product side. So if you're adding a product, then your reaction is shifting to the left. And the reason that heat is kind of in the product side for exothermic is because you are releasing heat, forming bonds, releasing heat, and if for endothermic reactions, you are using heat to break those bonds. So that's kind of why it's on either side of the reaction for endo and exo. And then if you're adding volume, then it's going to shift to whichever side has the most moles. So again, in this case, moles is just referring to the coefficient of your reactants or your products. And for this one, no changes. Catalysts will have no change. And adding or removing an inert gas, that also does not have any change to your reaction. All right, and this is just a little summary kind of differentiating kinetics and equilibrium. So again, no coefficients in your rate law, but coefficients are used in your equilibrium expression. This one tells you your speed of reaction, and equilibrium just tells you concentration of reactants and products at equilibrium. And kinetics, your rate law is written with only your reactants, but for equilibrium, your constant expression is written with products over reactants, so both of them. And for kinetics, your small k, and it does have units. For equilibrium, you have a big K, but this one does not have any units. And I wanted to say something real quick too for kind of determining whether it's first, second, or zero order. And there's a cool little mnemonic, so it's called time clear. And it basically is this. So this is going to be talking about time. And time is always on your x-axis. So this one is talking about concentration. And the rest of these are talking about your y-axis. So let's say you have time over concentration. That is going to be your zero order. But let's say you're talking about time over natural log. Then that is talking about your first order. And this is talking about your reciprocal. So let's say you have time over the reciprocal of the concentration, then that is second order. So if you ever are confused about telling a graph if it's like second, first, or zero order, just use that mnemonic time clear and then you can figure that out. All right, and I think that's the last slide before we get to our practice problem. So does anyone have any questions for me or Jessica before we kind of jump into our practice problems? All right, perfect. So I guess we can now go ahead and do our practice problems, and we will go ahead and put you guys in breakout groups for that one.
Okay, so I'm going to go ahead and get started then. So the first half of this is going to be equilibrium, and then the second half is kinetics. And we got it set up so that equilibrium is multiple choice and kinetics is free response. So you have a mix of both type of problems. So for the first one right over here, you guys have any guesses how we would write our equilibrium constant expression? So let's see. So when we're writing this, we want to do products over reactants, right? But is this equation ready to write an expression for, or is there something that has to be done with? Have you guys checked everything about this reaction? Yeah, it's unbalanced. So what do we do first? So if we put a 2 in front of the N2, would that balance it with the N on the right side? Let's first balance it, and then we'll go for the answers. Yeah. Okay, let's see. If we put a 2 over here, our N's are now balanced. What about our H's? Our H is balanced? Yeah. We want to put a 3 in front of H. So now we have 6 H's on each side and 2 N's on each side. So does this look balanced now? Yep. So now that we have a balanced equation, we can figure out which one of these it is. So you guys were right about the products over reactants part, but the coefficient, the exponent should change now. So what answer do you guys think it is? Yeah, it should be D. And that's because we got that little squared on the NH3 from the 2, and then that cubed from the H2 coefficient of 3. So I guess the key takeaway for this problem is instead of jumping straight to the formula, make sure you check your reaction to make sure it's balanced, because that balancing is gonna, change your expression by a lot. Even if like there's numbers in the problem, so you won't be able to get the right like KC if you don't balance it either, right? And they might be nice to you sometimes and balance it for you, and then they could stop abruptly for one question and then go back to balancing it. So super important. Always check your reaction. Don't assume it's balanced. Are we good on this one? Okay, cool. So regarding the same reaction in question 1, the values at equilibrium are the following. What is Kc? So anyone remember the reaction expression on the other page? So I believe it's something like Kc equal to NH3 squared, right? This should be a 3, I believe. Over N2 H cubed. We plug the number straight in now that we got the expression. Yeah, right? Because these numbers are the equilibrium, so they could just go straight into here. But again, notice how not balancing would have changed your answer. And you guys are correct, it is C. Any questions about this part? Okay, cool. So again, we're doing the same reaction as question 1 and 2. So now they're giving us values at some given point in the reaction. So are we at equilibrium? No, we're not. So are we doing a QC or a KC? Yeah, we do our case QC. Oh, I think The answer choices should be QCs in here. Ask for a QC. Wait, also, anyone remember the answer from the last slide? So we're going to need it for comparing. Okay, cool. I'm going to just write it down so we have it. 25.9 is our KC. So our QC, is it going to have the same or different expression as our KC? So it's going to have different numbers, but what about the expression? Yeah, the expression itself is going to be the same. So then we have it squared, NH3, and then N2. Sorry, it takes a while to write all this on the board. And then H2 cubed. You're going to take H2 over here, the N2 over here, and then NH3. Also, something to note, I know a lot of people like accidentally forget to do the exponents when they're putting it into the calculator. That's a common mistake to be aware of. Okay. And what are you guys saying it is, B? I agree. It is B. You're going to end up getting 58.46 for your QC. And if Q is greater than K, does that mean we have more products or reactants at this moment? Products, right? Because our expression is written products over reactants. So more products are on our right side. So we want to shift to the left to favor our reactants to bring that Q down. Does that concept make sense to everyone? Cool. Let's keep going. So now we have a new reaction over here. We have to, what do we do first? Have we checked the reaction? Yeah, we want to make sure we balance it if it's needed, right? So let's check our reaction. Does it look balanced? Do you guys think our reaction is balanced or no? Yeah, it's balanced, but it's always important to check. Don't assume. Okay, so yeah, how do you know it's an ice table? So these values over here, are they at equilibrium or are they something else? They're initial values, yeah. We want to go from our initial and figure out our equilibrium values. Yeah, exactly. You guys got it. So that's our like Q. Okay, so we're going to say we have 0.6 of carbon salt disulfide initially, and then we have 0.95. What about for our product? I should have wrote small, shouldn't I? I'm going to just shift everything over so I have space. What about for our products? What are our initial values? Based on the wording. 0, yeah. If they don't give you an initial value for products, you're going to assume it's 0. Everyone always goes so fast. Already at the answer? What number are we on? 4. It is B, but we're going to do the whole thing just to make sure everyone gets it. Oh, don't apologize. It's great that you're so far ahead. Okay. So what's next? How do we do our change? Are we gonna do positive or negative for the reactants? Yeah, so this is being recorded. It's gonna be on the peer tutoring like slide or not slide, but like tab, that you enter to get here. So the reactants are negative. How come? Did you lose anything from the product side? Is there anything to lose? Yeah, exactly. So should this be negative x? Or is there something I'm missing? Coefficient, exactly. Exactly like stoichiometry, you're going to consider that for every 1 mole of carbon disulfide, you could end up with 3 moles of chlorine. And that's why you add the coefficient in. Because for every 1 mole you lose of that, you lose 3 of that. So don't forget that concept. And positive x on this side. Cool. Great job, guys. And then for equilibrium, we just combine our initial plus our change. We're going to do 0.6 minus x, 0.95 minus 3x. Yeah, so basically if you're given concentration for everything, so all your products and all your reactants have concentrations, you have to figure out if this reaction is occurring in forward or reverse. You do that by finding your Q, like you were saying, Matthew, and then comparing it to the K. And it's the same idea as what we were doing last problem. If your Q is greater than K, you have more product, it's going to go the reverse direction to make it more and have more reactants, and vice versa. Does that make sense, that concept? Yeah, and usually problems like that are going to be when you have to whip out your quadratic formula, which isn't very fun. I probably won't give you many quadratic formula ones on the exam, because they're just really time consuming. Okay, now that we got this, what's next? We found our thing. Where do we go from here? So we find x. And how do we know it's 0.25? Yeah, it's given carbon chloride, or not carbon tetrachloride. Exactly. We know this one over here represents carbon tetrachloride. Carbon tetrachloride at equilibrium equals x, therefore it equals 0.25. So x is 0.25. So now we could take the one that corresponds to chlorine, which is going to be this one, 0.95 minus 3x, and we're going to plug this in for x. Yeah, and then all of that gives you, like you were saying before, B. So great job, everyone. Any questions on this one? Cool. Oh, are you taking biochem next year? I see 20 amino acids. Yeah, I'm in that right now. Yeah, 20 is a lot. Yeah. It's okay if you're good at memorization, but it's hard if like there's a lot to memorize for that. But back to Gen Chem, I guess. So the Kc for the given reaction is 26.7. And if the new reaction is S, then what is the Kc? So what's happening to this reaction? To take it from the original to this one. What's the changes? Yeah, exactly. So you're doing times 3 for the coefficients, and then you're flipping it. So what does that do to the Kc? We know coefficients equal exponents, right? The answer is A, yeah. So basically what you're doing is you're taking 1 over Kc and you're raising it to the third. Yeah, you could also do it in parentheses this way. An order operation dictates the, you do the third first and then 1 over. Does this part make sense? I think the easiest mistake to make with this problem is to forget coefficients mean exponents. So don't accidentally multiply. I feel like that could be like something that could happen if you're working through this problem really fast. And also remember that reversing is not a negative, but it's 1 over. It's the reciprocal. Okay, cool. We're making progress. So next, we have this reaction. If Kp for the reaction is 48.2 at 28 degrees Celsius, then what is Kc? So what formula do we use for this problem? I had covered it earlier. Yeah, exactly. Kp equals Kc RT over raised to the delta n. So let's find delta n first. So how many moles do we have on the right side? Three. And on the left side we have 2. So together we get 3 minus 2. So equals 1. Okay, what about T? Is 25 degrees Celsius ready for this formula? No, yeah, because our R constant has a unit in Kelvin, we have to make sure we're converting our temperature to Kelvin. Can't stress that enough. So 25 plus 273, right? Which should give us a temperature of 298. In Kelvin. Anything else we have to find, or are we ready to put it in the formula? We ready? Yeah. So what's our R, by the way? You don't remember? So it's a constant. Yeah, it's going to be 0.086. Oh, 8026, I meant to say. Oh, just looking up 8026. Okay, that's my ugly way of writing it out. But here we have it. You can memorize the R constant because they'll give you the constant, but you do need to memorize the formula. So after that, it is A. Any questions on this one? So N is positive because you do the 3 minus 2. So the product moles minus the reactant. So when we plug it in, it's just positive. So there's no negative in the formula. Does that make sense, Nehal? Yeah, no problem. Okay, next one. So given the same reaction as question 6, let's go back to question 6 for a second. Actually, no, let's go back. So given the same reaction as question 6, what would happen to if SO2 were added? So let's go back and see what SO2 is, where SO2 is. Here it is on the right side, so add it. What happens if we add something to the right side? Yeah, you gotta have a leftward shift. Exactly. So you want to rebalance it. You're adding more to the right side, to shift left to add more to the left side. Okay, now let's go to, let me see. So we're not doing anything to O2. O2 is staying the same. SO2 is going up, but to balance that, we're having a shift leftward. And that's causing this one to increase. O2, like, if they don't tell you anything, not anything's like, unless they tell you something's happening to this one, like nothing's happening is the assumption. Because if O2 increased to compensate for the SO2 increase, there would be no point in shifting to the left, right? Because we're already compensating on the right side. Does that make sense? Okay, cool. So now 8 says, so given the same reaction as question 6, so we're going to go back there. What would happen if it were to be heated? So we're adding temperature. So what's important to know when we're talking about temperature? Yeah, EXO or ENDO. So how do we know if it's EXO or ENDO in this case? Yeah, forming or breaking bonds. So in this case, you are breaking bonds. So this is a decomposition. SO3 is being broken into SO2 and O2. So breaking bonds means we have to absorb heat, right? Absorbing heat is endo, like you guys are saying. Endo means heat is written as a product or reactant? Reactant. So I'm going to write H that to represent heat. So if we're heating it, we're adding it to left side. Where is it being shifted? To the right, exactly. Derecha. Exactly. Any questions about this one? Clear? Cool. So now we have 9. So we're on kinetics now. So which EA represents the rate determining step in the following diagram? And where does the intermediate exist? So there is an EA. Yeah. So a higher activation energy. What does that mean? Why does a higher activation correspond to a slower reaction? Yeah, it takes longer to overcome it. If you're thinking of it like a literal hill, if the hill is long, it takes longer to climb than a small hill. So higher activation energy is going to correspond with the slower step. And you're right, the intermediate exists over here. And the reason for this is because to get the reaction going, we first have to overcome the EA. So the reaction starts after we overcome it. So over here, we're making the intermediate. Up here, we're going to get ready to consume it. Oh. Because in the second reaction, remember, because the intermediate doesn't exist in the total reaction, the second one involves consuming it. So the first one makes it, second one consumes it. It exists in the middle. That's where you'll have it. Any questions there? Cool. So now we're going to determine a law experimentally. So how do we do that? What are we determining here? Yeah, we're going to use the data, and we're going to find the order of each of the concentrations, right? So rate equals the concentration of x raised to some exponent. We don't know what. So I'm going to just write n times. Oh yeah, I forgot. My bad. I forgot to write down the k. You're right. You're right. And then y raised to some exponent. Also, I don't know. What's the next? B. So now we have to figure out the exponents, right? So we can do that by keeping one of the concentrations the same. So between experiment 1 and 2, x stays the same, while y, it doubles. So what happens here to the right? It also doubles. So what would do for the order of y? Yeah, it's first order. And yes, so this is going to be posted, the recording, on the peer tutoring section. I don't know if I post the slides. Yeah, no worries. But the recording of the lecture and this session, us going through it, will be posted. So you can just watch that. And then the next step is for figuring out the order of x, right? So now we're going to look where y stays the same. So that's between experiment 2 and 3. It's 2, 2. But then for x, it changes. So over here, x is becoming half. Well, the overall rate is being 4. So this indicates what type of order. Oh, it's going to be on the YouTube channel. My bad. Yeah, that indicates that it's being doubled. Because, to get from 1/4 to 1/2, that's how we do it. So that's our overall rate. And that's how we come up with it experimentally. And sometimes they may include another concentration as well. It'll be a little more complicated if you have 3, but it's the same step. Any questions so far? Okay, cool. So what type of problem is this? What concept is this testing? Yeah, it's half-life. So the integrated rate law, specifically half-life. So anyone know the formula for the first order reaction integrated rate law, and then for the half-life formula for it? Yeah, one, exactly. Exactly, those are the two formulas we're working with. So what's the first step to figure this problem out? Any guesses? So there's two ways to do a problem like this. And that's because we have a percentage that gives us an even half-life, 87.5%. So I'm going to show you both of the ways. So the first way is, you can start with finding out how much is left out of 100. So 100 minus 87.5 is going to give you 12.5%. So now we have to figure out how many half-lives it takes to get there. So if we have 100 and we half that, we're going to end up getting 50, right? And then if we have 50, we get to 25. And then if we have 25, we get to 12.5. So let's count the half-lives. We have 1 over here, 2, 3 half-lives, right? So then we now have how many half-lives it takes to get to 87.5%. 3. So now if we know it takes 3 half-lives, and we can find, so the original formula being for half-life or a first order, 0.693 over k equals the time it takes for 1 half-life. And we're given a k of 62.5. What do we get? If we do this division. Anyone with a calculator? Yeah, you get something like 0.011. But we have 3 of these half-lives, right? To get to 87.5% complete. So what do we do with this number? Yeah, we multiply by 3. So you're going to end up with 0.033 for how long it takes for this reaction to be 87.5% complete. And that's the first way we could do a problem like this. And then we're gonna do it the second way. Yeah, we could also set up the ln way. So I want to show you guys both of them since you may be more comfortable with one over the other. And you can't always do this like the method I did the first time. You can only do it if you have even half-lives. Like if for example, it said how long does it take for the reaction to be 77.2% complete, you can't really figure out how many half-lives are easily in that. You would do it this other way. So yeah, you would do it exactly how Neha has it written. And you would plug in, the formula again would be the concentration at the end over the initial A naught equals negative KT. So we want to solve for T. We plug in the K over here, and we have to figure out the AT and A naught. Again, we could do this with theoretical values. Yeah, you could end up getting 0.0333, Caleb. Exactly. So because it's a percentage, we could just think of it as a relation. We don't need actual values. So again, you want to figure out how much is left from 100, maybe 0.5%. You want to convert it this time to a decimal. So you're going to do 0.125. So when we do the math, we don't want to work with percentages. We always convert them to decimals. So 0.125 is how much we end up with, or how much we have left. And then we plug that in, just like Nehal has it. And yeah, that's what we have. Any questions? Okay, we're moving on. We're almost done here. So just a little more to go. Yeah, there's a conceptual one. Yeah, it speeds up the reaction specifically by lowering their activation energy. So I'm going to give you a picture. So how would this curve look if we added a catalyst? Yeah, exactly. We're going to lower it. It's going to come down. But it doesn't change our reactants or our product concentration, right? We're going to always come back to the same spot. It's only EA that's being affected. I just want to stress that point. And they're useful exactly for helping maintain metabolism. They make our reactions a lot more efficient. Like I was saying in the beginning, we don't want to run reactions, even if they have a good output, if they take too long, because then they're just not usable. You know, humans have a limited lifespan, so we don't want to wait forever for a reaction to occur, even if it gives us like a lot of good stuff, like, I don't know, a cancer drug. So maybe we could speed up that reaction though by adding a catalyst, and then we make it feasible. Because we still remain with that like output we wanted. We just, now we can do it faster. Yeah, and enzymes in biology are a great example of really important catalysts. We couldn't have alive without enzymes in our body. But you guys don't have to know the specifics on how enzymes work unless you're in bio right now. And then, yeah, that would be important. So some reactions we do want slow in the body. Yeah, I mean, our body wants to be controlled really specifically. Like homeostasis is super important for our bodies. So we don't want everything to happen as fast. Not everything needs an enzyme, but a lot of stuff we do want to happen fast. And so that's where enzymes come in to make other reactions in our body much faster. But the concept of enzymes will definitely come up more in bio than it will here. Okay, so the next one. This one's a little tricky. So the rate law given over here was experimentally determined. So given the following mechanism, how can the identical rate law be written from its rate determining step? So which one's the rate determining step, first of all? Yeah, it's based off the slope. But, okay, now let's say I write rate law. It's going to include this intermediate, won't it? And exactly, yeah, that's how you would write. But is that the same as the rate law that they determined experimentally? Yeah, so it doesn't look the same, but we can make it be the same. So that's where this fast equilibrium comes in. So you can only do this when you have a fast step preceding the slow step. And basically what will happen is that when you get to the intermediate, you're going to end up making it in reverse as well. And so we can write a rate law based on the forward reaction of the fast equilibrium and the reverse reaction. And to give us rate law, we can then plug in to the one Caleb wrote in the chat. And so let me show you guys how that would work. And I don't know if there'll be any problems like this on your actual exam, but I wanted to give you an example because I noticed the book had something like this. If we're saying rate is equal to K, right now, N2, O2, and H2. And let's say this K right now, it's not the same reaction as the rate law, so I'm going to give it a different name. I'm going to say it's K2 because it doesn't match this rate law yet. So now I'm going to write a rate law for the forward reaction of the fast equilibrium. So how would that look? So I'm going to write a rate equals, and I'm going to name this K, K1. And I'm going to write no squared. And I can use the exponent here. This is not our final rate law. This is just the one we're writing temporarily. But I can use the exponent since it's a elementary step. And then I'm going to write it in the reverse step. So the rate in the reverse is going to be the K inverse, the negative one, and then N2, O2. And this rate of the forward and the reverse one is double-sided arrows, so you can say that they're equal to each other. And when I set them equal, that allows me to isolate my N2, O2, so I could then plug it into the rate Caleb has, and we wrote down here with the intermediate, because we don't want the intermediate to be in our final one, since intermediates are eventually consumed, so it doesn't represent an accurate rate. And so to get N2, O2 isolated, we're going to want to divide by the reverse K, the reverse reactions K negative. And then we just have N2, O2 now. And when we have just N2, O2, we can now plug it in, kind of like substitution in algebra. So all this is going to go into here. So now we're going to end up getting K2. So that's the K we put in front of this reaction, since it's different than the one we'll get eventually because of the intermediate, times K1, the one we had for the forward fast equilibrium, divided by K negative 1, which is the reverse of the fast equilibrium, will give us NO squared and times H2. So I don't really have room to write H2, but basically we're going to have this, but with K2 times K1 over K negative 1. So basically, I think this equal should have been right over here. Rate law is equal to K. There. Is anyone highlighting the words? Anyways, or is that me? Okay, that was me. Never mind. So now when we got it like this, we can say K is equal to K2 times K1 over K negative 1. But we got it substituted to be in the regular experimental rate law formula. But that basically shows how you can take an intermediate in a rate determining step rate law and then change it into an experimental rate law. And all of this complicated case ends up equaling the K in this rate law. But if you had these the K2, K1, and K reverse to work with, then that's like how you would be able to find the ending K. Does this make sense, the process of this? Yeah, so from what, like, I don't know exactly what your professors say. If your professors will let you write a rate law with an intermediate, then you can. But if they don't, they want you to substitute it this way. Yeah, exactly. And so if they're not clear, then this is how you're gonna go about the substitution. And it only becomes relevant when you have a fast equilibrium happening before the slow step. Usually you won't have something like this, and then you won't have an intermediate to deal with. But in the case that you do, you have to go about the substitution this way. So you want it to end up being a rate law without intermediate. Does this make sense how we go through the process? Okay, cool. And they're equal. Once you do the substitution, they're equal. You just have to keep it. And you have to just do it. Yeah. Okay, another conceptual one. How does refrigeration affect reaction rate? Yeah, it slows it down. We don't want our food in our fridge to spoil, so that's why we refrigerate it. We put it in a cold environment. The cold slows down our reaction. Exactly. Any other examples of like reaction rates in real life? Iron rusting. I haven't heard of that one. Um, yeah, boiling water, that speeds up. There's one, if you might have seen this in your textbook, but it mentions how you have an avocado, and usually it would brown pretty fast, right? If you leave it out in the air. But if you add lemon juice to your avocado, it slows the browning process, right? Have you guys heard of that example? Yeah. The same thing with other fruits. Adding lemon juice slows them from browning, like with apples. There's tons of examples. So I'm not actually sure what the mechanism of that is, but it's just an example of like how reaction rates are modified in real life and like how it's useful even. But I'm not exactly sure on the mechanism, but you could definitely Google it. I'm sure there's a ton of information on how that works, like chemistry wise, and it would really be interesting to hear about if you find out. Yeah. Oh, citric acid keeps fruit from browning because it is full of ascorbic acid. Cool. That makes sense. So it's like a La Chatelier's principle thing. No, not Le Chatelier's. I don't know what I'm saying. That's equilibrium. Anyways, next one. So given the decomposition reaction, HI decomposes into hydrogen and iodine. You could write the rate law, right? And they're giving you. So can you or can't you? No. Why would I be able to? So actually, usually you would think you can't, but they give you a clue here. They give you something for the K. Yeah, the units of K tell you what order the reaction is at, right? So we know 1/2 means it's a first order, right? So if we know it's first order, then we don't have to worry about experimentally finding it out. They told us, they slipped in that little hint. So I just want to throw this problem in because like it's a very small detail at the very end, but that unit of K is going to tell you the order. So you don't have to worry about like taking coefficients because you can't. You can't just be like for example, if you wanted to balance this problem, you would have put a 2 in front of HI, right? But you can't just be like, oh, this is second order because there's a 2. It's based on the units of K in this case. So we can write it in this case. For a sneaky way, they might be able to throw it in for you guys. Make sense? Any questions about this one? Cool. So then we have our last problem. So for our second order reaction, we have this formula. If the initial concentration is this, and the concentration is that at 128 seconds, what is the value of the rate constant? How do we do this? Yeah, we have to use the integrated rate law. What's the clue here? Yeah. So for a second order, it is that reciprocal formula. But how do you know you need the integrated rate law? So it's not a half-life specifically. They're asking the rate constant, but it gives you an initial concentration and it gives you a final concentration. It also gives you a time component. If you were trying to find a K constant from a rate law, you don't have a time component in your rate law, do you? You have rate that has a molarity over seconds, and you have K that could be 1 over seconds, but we don't have K in this case. And we don't have anything just seconds in our rate, right? Yeah, it's 0.39. You're right. When you do the plugging in of everything, you're going to end up getting 0.39. Also, some note is I gave you it in seconds, but I could have given you something like 5 minutes. Could you use minutes in your formula? Yeah, I mean, in this case, I guess you could find a K with minutes. But usually we work with seconds, okay, just because our rate law is molarity per seconds. If they, for example, had another problem after this, where they wanted us to find a rate law, or like a rate. Yeah, so you basically use what's given, but if you had another problem following up that was talking about rates and had molarity per second, just make sure you know what you're using. Don't forget. And the same with half-life. Like you have to be consistent. So if you there's a follow-up problem that has something with seconds and you use minutes, like don't forget to convert your minutes to seconds. Or if the answer choices, for example, have K in seconds, then make sure you keep that in mind as well. So it's a multiple choice problem for your exam. So you want to be aware of what unit you're putting in. Does that make sense? Yeah. Cool. And that brings us to the end of today's review session. Any questions? Oh, yeah, sure. You can see that, Vicky. If we do the rate of forward divided by the rate of reverse to get K are the ones we divide the little k. Yeah, so when we're talking about kinetics, we're always talking about little k's. And when we're talking about equilibrium, we're talking about big Kc or Kp. And I'm assuming you're talking about the problem where we were 13, since when we were substituting. Is that what you were saying? Yeah, it would be little K1 over K minus 1, just like it's written here. Is that what you're asking? Okay, cool. Where will the review recording be posted? Yeah, no worries. If you scroll, actually, not sure you'll be able to see it. I'm gonna re-put the YouTube link then in the chat, and the YouTube should have it, I believe. If I can find it. Did someone put it there already? I can't tell. Oh, there it is. Yeah, cool. That's the YouTube link. And it should be there from the beginning of like the lecture and stuff. Yeah, you too. No problem. See you, everyone. Good luck on your exams. You're gonna do great. All of you seem very knowledgeable. Yeah, of course. I hope it was helpful.
Hello?
Hi.
For number 15,
Yeah?
how come it's solvable? Because I immediately thought it was not, because it was a multi-step. It looked like a multi-step reaction, so the rate law couldn't be given. It was a multi-step. I thought the rate law couldn't be given.
So basically,
I mean, I understand how you got the answer, but I immediately thought it was a multi-step.
so you thought this was like the total reaction and not elementary step?
Yes.
Yeah. So usually that would be the case, and this can be the total reaction. If not, the thing is, in this case, if it is the total reaction, usually why we do a rate law based on the total reaction, like the reason we can't do that is because we don't know the order. We do know, like, for example, that the rate law is based on just like reactants, but let's say they didn't give us the unit of K, like we wouldn't be able to figure out the order. We'd be like, the order is an X. But in this case, like they give us the information. Like it's the same as saying you have this like reaction and it's has an order of 1. So I imagine that was written out for you. Does that make sense? Like, for example, if it's not written and balanced it, you can just be like, there's a coefficient of 2, I'm gonna bring that down, that's the thing. That wouldn't be right. You can't figure out coefficient, like the order of the rates based on that. But if they're giving us this, I think that's their clue that they're telling us that this is order of the reaction. It's kind of like determining experimentally, like someone did it for us already, and they're giving us that information.
Okay, I understand now. Thank you.
No problem.